Welcome to the systems session of POPL. This is Arthur Morin. Our first speaker is Matthew Kolosick, who kindly agreed to join us for an in-person talk rather than a remote one. And he's going to tell us about isolation without taxation, near zero cost transitions for WebAssembly and SFI.
Excellent. Can we hear me? I can. Cool. We good to start? Excellent. So hello, my name is Matthew Kolosick. I'm a PhD student at University of California, San Diego, and today I'm going to talk to you about our work on speeding up software sandboxing. So third-party code is everywhere, from media libraries and web browsers to cloud computing to even things like PDF rendering in iMessage. Unfortunately, there's a lot of danger in this, which is that these third-party libraries are typically, for speed reasons, written in unsafe languages like C or C++. Unfortunately, this means that a bug in those third-party libraries, such as a bug in libvorbis, can lead to a potential security issue in Firefox itself. This also happened in Chrome recently with the FreeType library, where a heap buffer overflow in FreeType led to a security vulnerability that Google was aware of being exploited in Google Chrome itself. Even more recently and more dangerously, these 4 lines in a third-party library used for PDF rendering and iMessage led to a zero-click exploit that were targeting a Saudi activist. We worked with engineers at Mozilla to help solve this problem in Firefox by sandboxing this third-party code. So moving from a world where we have these potentially buggy third-party libraries leading to security vulnerabilities in Firefox itself, to one where we've isolated out these third-party libraries so they can no longer lead to security vulnerabilities for Firefox. So how do we do this currently? So we do this using a technique called software fault isolation. And this works by adding enforcement to the potentially buggy code. So we take something like a sandbox libjpeg, compile it through an SFI compiler, which does things like adding instrumented reads and writes, an instrumented control flow, ensuring that we have a secure produced output at the end that can be safely linked with Firefox. Unfortunately, this isn't the entire story, because at that low level we're actually linking with Firefox, we have a number of shared resources at that machine level, such as a call stack, callee-save registers, and scratch registers. And to deal with making sure that these are handled securely, traditional SFI tools insert a set of wrappers that we call heavyweight wrappers to ensure that these are used securely. Unfortunately, we found that these heavyweight wrappers have a number of problems. First off, they're expensive. They happen at every context switch to and from the sandbox code and the application itself, and must clear and restore all shared state. When we started adding SFI to Firefox, we found that an optimized version of these wrappers added up to a 20% overhead for the wrappers alone, and the original unoptimized version of the tool we were using added up to a 900% overhead. Further, they're hard to implement. There's a lot of different processors, conventions, and they need heavy optimization in order to not incur such significant costs as we originally saw. But this doesn't work well with the fact that you can't miss any details, and if you do, such as these bugs from Knackle, these lead to potential security issues in your overall system. Our solution to this is something we call zero-cost transitions. So we build on the insight that SFI tools already add enforcement to guarantee memory isolation, ensuring that the code is sandboxed. And we ask the question, could we add some extra enforcement to actually remove the need for these heavyweight wrappers? And we answer this question by defining a set of zero-cost conditions that capture the extra invariance that we need to guarantee the safe use of these shared resources, thus letting us completely remove those heavyweight wrappers. In our work, we do this by building 2 different zero-cost SFI systems, one based on WebAssembly, where we take code compiled to WebAssembly, compile it through a compiler to native code, and then remove that from the trusted code base by building a verifier for that native code, and then also a direct implementation using LLVM-based systems. So in the rest of this talk, we're going to step back, first looking at what are those extra invariants and what are these zero-cost conditions. Then we'll look at how we enforce them in our tools. And finally, we'll look at what the performance trade-off of adding this extra enforcement in exchange for removing those wrappers is. So first, let's look at what are those zero-cost conditions. And to answer this, we actually need to step back and look at what does it mean for a boundary to be secure. Throughout this, we'll be looking at this example code here, which is a sample, very simplified sandbox function f, which is we're going to pretend being called by Firefox. It doesn't do anything interesting, but we're going to use it as our example. Now recall that there's a bunch of shared resources at the machine level this is operating at, such as a call stack, callee-save registers, and scratch registers. Our security properties then look like things that say, here's what the sandbox code cannot do. And in particular, it cannot do things like clobber shared resources or read secrets from shared registers. We're going to look at both of these in turn, but we're going to start by looking at not being able to clobber shared resources with callee-save registers. So to step back to make sure we are all on the same page, callee-save registers are a platform and calling convention specific set of registers that, if used by a function, are supposed to be restored by the end of that function. So in this particular function f, R12 is a callee-save register, so it is used, so therefore it must be saved and then restored across the function. Our security property then is, across calls into the sandbox, all callee-save registers must be restored. Unfortunately, with traditional systems, the SFI enforcement doesn't guarantee that code will behave like f on the right. And this means that this picture of the code inside the sandbox instead looks more like this, where it knows it's memory safe, but doesn't know anything past that. It doesn't know which registers f uses. It doesn't know if it saves or restores them. And this is why it has to insert those heavyweight wrappers, which save and restore every callee-save register, because it doesn't know which ones are needed. Our second class of security properties relate to confidentiality and not reading secrets. So in particular here, the problem is that scratch registers in Firefox may have application secrets in them or important application context. And if this leaked into the sandbox library, that would be a problem. So our security property then is the sandbox cannot read any of those application secrets. But once again, in a traditional system, there's no such guarantees about how the sandbox code behaves this way. So heavyweight wrappers must clear every single scratch register, no matter which ones are used. This leaves us in a world today where we have, on every call into a sandbox library, saving and restoring every callee-save register, clearing every scratch register, and then some more on top of that. But this is the case even when the code inside the sandbox looks something like f, where it actually does things like saving and restoring the callee-save registers it uses, which means that the wrappers are duplicating that code. And further, for f, it doesn't actually use any of these other callee-save registers, so this is just unneeded work. To alleviate this issue, we define a set of zero-cost conditions which guarantee that things behave like f and behave properly internally. So this takes advantage of the fact that this structure is generally related to calling conventions and generally actually already exists in existing code. So the zero-cost conditions then capture the invariants necessary to ensure that this behavior holds on the code, thus letting us remove those heavyweight wrappers. So we're going to look at 3 of our conditions related to this. So the first one's going to be type-safe function calls, and the next 2 are going to be related to the resource usage itself, with callee-save register restoration and information flow control. So first, let's look at our first condition, type-safe function calls. So we require that each sandbox function has a type, including internal functions like g that f calls within the sandbox. So for instance, f takes no arguments. G takes a single argument, which is passed in the RDI register. Our invariant then is that the function arguments must be initialized before calls. So f calls g, which takes an argument in RDI. So RDI must be initialized before calling g. Further, this is a direct call, but we require that indirect calls are checked dynamically generally to be to an appropriately typed function. And this serves as a baseline that guarantees each function starts in a known state. Our second condition that we're going to look at then deals directly with the actual resource usage with callee-save register restoration. And this one's fairly straightforward. We require that each sandbox function must restore the callee-save registers. But in particular, since we can now reason at the function level, it just needs to work with the ones that it itself deals with. So f uses R12, so it must save and restore it. We can already see how this guarantees that f will do the things that the heavyweight wrappers were trying to do, so we can already start deleting those. With information flow control, the problem there is that a secret might be stored in, say, a register R12 from Firefox. F uses R12, so we need to make sure that that secret does not flow to anything in F, and in particular, that secret cannot be used in F. We generally deal with this by initializing before use, so any register must be initialized to some value from the sandbox before it can use it. This ensures that the Firefox secret cannot actually make it to that third line. And we can see once again how this obviates the need for the heavyweight wrappers to clear every register, because we just deal with the one, F it deals with the ones that it needs to deal with. Stepping back again, so we started in a world with heavyweight wrappers because code looked like this, and we didn't know what to do with it. Then we added our zero-cost conditions for extra enforcement and structure to make sure that we actually could see inside and see what the code was doing. which lets us safely delete this wrapper code while maintaining security. So next, we're going to turn and look at how do we actually enforce these zero-cost conditions. And we're going to look at our main system where we implement zero-cost SFI using the WebAssembly tool. So here we first take any code through any compiler compiled to WebAssembly. We then use the Lucet WebAssembly to native compiler to produce native code that we will eventually link. But this is just a compiler that someone else develops, so we don't want to have to rely on it for trusting for our security properties. So we remove it from the trusted code base by building a verifier that operates on that produced assembly to then verify that code, and only then do we link it with Firefox. So we're going to first look at how we actually use WebAssembly to enforce these zero-cost conditions. So WebAssembly actually works really nicely for this because it is a low-level intermediate representation built with this sort of security in mind. And in particular, that means that by specification, WASM requires that compilers enforce things like memory isolation, type-safe function calls, and that all variables are zero initialized, and several other properties beyond that. And we can already see how this lines up with our zero-cost conditions. And in fact, it happens to line up with all of our zero-cost conditions and then some more properties. So we basically just get that all of our properties are guaranteed by any WebAssembly compiler that is spec compliant. But we don't want to rely on that any WebAssembly compiler to exactly get things right when we're dealing with security. So we build a verifier for the actual produced code, and this extends our previous work on a VeriWasm verifier. VeriWasm previously just checked SFI properties of code produced by Lucet, which means that it checks things like instrumented reads and writes and a limited version of control flow isolation. We extend it to check the additional properties that we need to ensure zero-cost conditions are maintained. Fortunately, we found that these extra properties can actually basically be checked by just tracking data flow. And in particular, we do this through just 3 abstract states. So the first of these, uninitialized, captures when something is a potential application secret, something that is, from the sandbox perspective, uninitialized. On the other side, we have initialized data, which is something that came from the sandbox and is therefore safe to use. And lastly, we have this extra value, which represents something as both a potential application secret, but also the initial value of a callee-save register that must be restored. So we're going to look at how this works by walking through an example with our function f from earlier. And in particular, we're going to be checking 2 of our conditions that we need in order to ensure that this is safe. So first, g takes a function, a single argument in RDI, so we need to check that it's initialized. And second, we need to check that all callee-save registers are restored before we return from this function. So when we begin this analysis, we know that R12 is equal to the initial value of R12. So after we've pushed it, that is now stored to the stack. In the next line, we've initialized R12 to a constant, so we know it's initialized to a sandbox value, which means that RDI is also initialized, which means that when we reach the 4th line, we have now passed our check and ensured that the argument to G is initialized. On the 5th line, we now know that the value of R12 has been restored from the stack and has been restored to, in particular, its original value, which means that all callee-save registers have been restored at the end of this function. In contrast, if we remove this line, or if the compiler hadn't added the 2nd line, which ensures that R12 is initialized, our compiler, after what no longer exists there, would still have that R12 was the initial value, which is a potential application secret, which means that RDI is also uninitialized and based on potential application secrets. So we would reject in the 4th line this program as it's a potential leak of application secrets when we call G. We validate VeriZero both in theory and in practice. So on the theory side, we build up a model and then build a logical relation for functions that meet our zero-cost conditions, then prove that verified code is in this relation, which then guarantees that verified code can safely remove heavyweight wrappers while maintaining our security properties. In practice, we first fuzz tested VeriZero with 100,000 random C programs that we compiled through Lucet, and then tested also on representative examples of real transition bugs, such as those we pulled from the NACL issue tracker earlier. From there, we actually verified the sandboxed Firefox libraries that we were sandboxing for Mozilla. And then lastly, VeriZero has also been deployed in the Bytecode Alliance's Wasm time toolchain. So lastly, we're adding some extra structure, but in return, we're getting to remove these heavyweight wrappers. So we need to look at what the performance trade-offs thereof are. And we do this by asking 3 different questions. So first, in general, how much overhead do these heavyweight wrappers actually add when we're executing sandboxed code? Secondly, what is the end-to-end overhead of enforcing these zero-cost conditions with WebAssembly? And then what can the overhead of a purpose-built zero-cost SFI system be? So let's start with the first question. So here we actually have to answer this question in terms of how frequently are we switching between application and sandbox library. And we do this using a sandbox libjpeg. And in particular, we do this because Mozilla Firefox makes one call into the sandbox for each row of the JPEG image, which means as we increase the width of the image, we can spend more time in the sandbox per call, and vice versa. We then use our zero-cost WebAssembly implementation as a normalized baseline and compare to an optimized heavyweight transition system for zero cost. And we find that these heavyweight wrappers add up to a 29% overhead in the worst case. We actually have to rescale our axes to deal with Lucet because it has such bad performance in terms of the heavyweight implementation, and it adds up to a 900% overhead in the worst case. Our next question deals with what is the end-to-end overhead of implementing these zero-cost conditions with WebAssembly. And this work actually began because sandboxing the libgraphite font shaping library was too slow to actually include into Firefox. And this occurred because the initial heavyweight wrappers for Lucet added up to a 600% overhead versus unsandboxed code due to these heavyweight wrappers. When we realized that we could actually just remove those while maintaining security, we found that zero-cost transitions safely brought this down to an 80% overhead, letting us get libgraphite sandboxed in Firefox. Unfortunately, 80% isn't great. And the problem here is that Lucet is kind of slow as a compiler and doesn't optimize that heavily. So recently, since this work, we've actually switched to a different WebAssembly compiler called Wasm to C for sandboxing in Firefox. And this gets us things like significantly faster enforcement and let us sandbox more libraries. Lastly, we looked at what the potential overhead of purpose-built zero-cost SFI could be. So here we built a tool called Segment 032, which uses the zero-cost conditions as a design tool from the ground up. And in particular, we use x86 32-bit segmentation for memory isolation and protecting saved state, such as callee-save registers. And then from there, use mostly off-the-shelf LLVM hardening passes to just walk down our checklist of properties, ensuring that they're enforced in compiled code. Here we compared against 32-bit NACL implementation and also an idealized heavyweight transition system where we assume that the actual internal enforcement costs nothing, but it still has to do heavyweight transitions, and then compare to our tool. We find that NACL has a 92% overhead end-to-end versus unsandboxed code. Our idealized heavyweight system still has a 66% overhead just due to the heavyweight wrappers alone. This is again on libgraphite, whereas our segment 032 system only has a 22.5% overhead end-to-end. So that's our work on zero-cost transitions. We looked at how traditional SFI compilers don't add enough structure and enforcement, so they need these heavyweight wrappers. We showed extra invariants that we can enforce on our code to ensure that we can remove these safely, and then showed how to build a production zero-cost SFI system using WebAssembly and then a verifier to check that this is actually safe at the end. So thank you. I'm Matthew Kolosick, and you can find this paper at the link above.
All right, we have plenty of time for questions.
Mike Hicks, University of Maryland. I'm curious, how resilient is VeriZero to the choice of compiler? For example, if you just use GCC or Clang, I realize you wouldn't get the SFI parts, but I wonder if the zero cost conditions would be just as easily discharged from an arbitrary compiler.
It is unfortunately very dependent on the particular compiler used, just due to some of how we actually have to track the sort of behavior of things like storing and restoring of these saved variables due to just sort of like shapes of stack frames. So right now it's not very resilient to that.
Thank you for the very clear talk. My question is about kind of statically enforcing these kind of ownership over registers. When you were giving that part of the talk, it really reminded me a lot of Rust and of ownership over variables, over ownership over memory. Have you thought about if you can extend WebAssembly or extend this framework to kind of enforce these statically as part of the type system? Thank you.
We have not thought about that directly. So one of the things that, so sort of like ideally, like my ideal world is we like replace all this third-party code with Rust, and then we're like, cool, memory safe, don't need to do any of this at all. But right now, sort of how it ends up working is you do get something kind of similar with how WebAssembly works, because basically all of the WebAssembly variables are sort of in a separate memory space that actually is entirely disjoint from the like stack frames that deal with the actual like where you're saving registers and things. So you sort of kind of get that already, but in a different way.
We're going to take a few online questions. So one question from Max Wilsey is, instead of compiling the WASM to native code, could you just run it? What would the trade-offs of this approach be?
Yeah, so the problem with just directly running it in something like a virtual machine is that virtual machine actually will both have its own overhead, and all these sorts of VMs at the like boundary where they interact actually have a sort of similar issue with the heavyweight wrappers, where they have to mediate between the sort of VM setting and then also the like native code that is the rest of Firefox. So they would have both the VM overhead and a similar issue as the heavyweight wrappers.
Here's another online question from Benjamin Delaware. Where do the function type annotations come from? Are they automatically inferred, or do users provide them?
So we pull these. So our verifier just works over things produced from WebAssembly, and so we pull that information out of the WebAssembly. Actually has those types for the WebAssembly level functions. We basically pull it out after the compilation, where it's still reflected in the produced assembly.